I can't see my mouse. Can I minimize that?
Yeah,
Okay.
you can. Oh, you don't see the mouse?
Yeah, I don't know where it's going. One sec. I just want to check how to. I can't like.
Okay.
I hope everyone can see this now.
Yes, yes.
Okay, awesome.
Good, maybe let me just do a quick introduction so we can get started. So I'm really glad to welcome Suchitra Narayanan, who is visiting us from CFA. Suchitra has a bachelor degree, actually two, from UC Berkeley, one in astrophysics and another one in chemical engineering. She's currently an NSF graduate research fellow and PO scholar at the University of Hawaii and also working at Harvard CFA. So her research is co-directed by Jonathan Williams and Karin Öberg. She has done very exciting work on the sulfur problem, connecting observational, experimental, and theory work. And today she will be, I think, talking mostly about some of the experimental work. But she has a real interest in connecting to many of you on planet formation, solar system formation, cosmochemistry, and also sample return and analysis. So Suchitra, please go ahead. Take it away.
Thanks so much, Daniel, and thanks all of you, both in person and online, for being here. So today I'll be talking to you about organosulfur chemistry, specifically using experiments, theory, and observations. I'll focus more on the first two and then talk a little bit about my current observational programs. But I first wanted to just dissect what this title even means. When I say organosulfur chemistry, I mean a sulfur compound containing a CH bond. So the simplest of this would be HCS. But what I mostly focus on is methyl mercaptan. So this is what the structure looks like. This is the sulfur analog to methanol, which will be important. But just so you're aware, when I say methyl mercaptan, it's CH₃SH, or in some of these slides, it's abbreviated as MESH. And when I talk about the birthplaces of stars and planets, I'm talking about the evolution from cold dense molecular clouds to the different classes. So there's 4 class 0 disks where a protostar is embedded in its dust envelope. Class 1 where it's still surrounded by this envelope, but there's some outflows, there's an accretion disk forming. And then class 2 are our classical protoplanetary disk images that you might remember from ALMA, where you've reached, the pre-main sequence star has reached its final mass, but there's a protoplanetary disk. And then finally, class 3 disks, which are late stage. The parts that I'll be focusing on for my observational work will be the class 0 and 1, which are the embedded sources, because this is what represents the link between the sulfur-rich ISM and sulfur-poor disks. I'll talk a little bit more about why we have this sulfur-rich and sulfur-poor in a second. This is just a brief outline. First, I want to talk about why sulfur. So the building blocks of life as we know it depend on hydrogen, oxygen, carbon, nitrogen, sulfur, and phosphorus. And I said those in the abundances that they are in the universe. So sulfur is the 5th most abundant when it comes to these specific elements and 10th most in the universe overall. So it's a pretty abundant element. And it's important for us because it's into amino acids that we need to live. And methyl mercaptan is a precursor to these two. But it's also important in 2 other contexts. So one is astrobiologically. So it's present in amino acids, proteins, and lipids. And there's actually been a really cool discovery by Dimitar Sasolov and the Origins of Life Federation. That's a joint endeavor between Harvard, Chicago, Cambridge, and ETH Zurich. And they found that the early Earth, the RNA molecules that are the nucleobases actually needed sulfur substituted nucleobases. So where there's an oxygen, there's actually a sulfur. And that's what early Earth probably was made of. And this is quite important, which I'll bring up later, the reason why sulfur and oxygen are important. But it's important biologically, but also in terms of planetary habitability. None of this prebiotic chemistry can even occur if there was no presence of sulfur-bearing organics and a little bit of nitriles, but we do need this element in both of these contexts. And what don't we know about, what do and what don't we know about sulfur right now? So in terms of our most abundant elements with respect to hydrogen, OC, and an S. I show the gas phase abundance relative to H across a bunch of different evolutionary stages. So we have our diffuse ISM, two dense molecular clouds, our solar abundance, and our meteoritic. So and note that it's a log scale on the y-axis. This is oxygen. It's pretty stable. Carbon, nitrogen. And then when you go to sulfur, there's this in these ISM and molecular clouds, the relative depletion of sulfur with respect to the ISM abundance, it depletes by a couple orders of magnitude, which is not really seen for the other ones or not well explained at the moment, because the other ones, that depletion is accounted for in the ice constituents, but not for sulfur. But then we see in our solar system, it goes back up. We are pretty sulfur rich in our solar system relative to interstellar abundances. And so this problem was known since the 1990s as the sulfur depletion problem or missing sulfur problem. This is just contextualizing the basis of this thesis that I'm presenting. And in terms of our current gas phase chemical inventory, just so you have some numbers to know why this is so significant, we have over 300 individual molecular species, and 40 of these are detected in the gas phase. If sulfur is not in the gas phase, people were thinking it must be in the solids, it must be in the ices. So 300 molecules overall, 40-ish in the gas phase for sulfur. And then when we go to the ice constituents, these are the most prominent ones. There's only one sulfur-bearing molecule that has been confirmed in ices, OCS. We thought with JWST, with the ice stage program, we'd actually see a lot more of the inventory, but even then, we only have a tentative detection of SO2. So we have 300 plus molecules, 40 in the gas phase for sulfur, and only one, probably two in the ice. And so this was really surprising because if it's not in the gas, it must be in the solids, but in the solids, we only have this much. And notably, there's no detection of H2S, which is the most abundant molecule in sulfur-bearing molecule in comets. It's the 5th most in 67P. And this is also really surprising because there are a lot more sulfur-bearing molecules in comets like S2, OCS, and sulfur organics, also including CH₃SH. So the fact that we're not even seeing it with JWST and we've had it for, it's been observing for a couple of years now, that's been really surprising. And another thing is that all of these detections only account for about 4% of the cosmic sulfur budget. And so we're still not accounting for about 95-ish% of it. So where could it be? I just want to summarize what we know through observation. Sulfur is depleted in the gas phase relative to its cosmic abundance. These are the detections in the ISM. We have 5 in disks, so notably H₃CS, which is the sulfur analog of formaldehyde, is the most complex sulfur that we've seen so far, which is a 4-atom sulfur, and only one S-bearing molecule in ice. And this is how it connects to theory, in that astro observations provide spatial, thermal, and compositional constraints. So if it's so hard to observe, how can we model it? How can we understand it? We go to our periodic table and we just take a look at the metals. So this kind of hurts my chemie background, but since I'm talking to astronomers here, valence electrons are responsible for an element's reactivity. You might remember this from high school chemistry. So there's 6 valence electrons. And so modelers leverage the fact that these oxygen and sulfur have the same number, and so we can infer how sulfur-bearing comps form or react based on their oxygen analogs. And so there's the most complete gas-green reaction network is Loss and Caselli 2019, where they include both gas and grain surface chemistry. And they model, they can reasonably reproduce the depletion across different cloud environments. So I include 2 of them that I included in the first graph where I illustrated the depletion. Notably, they don't find H2S as a dominant sulfur carrier. They predict that most of the missing sulfur is an organosulfur species, but there's 2 important caveats. The model assumes that sulfur and oxygen react similarly, and it shows no evidence of sulfur chains or rings to form a significant refractory component. Now, this is important because we haven't found it in the ice. And one of the reasons why people thought it could be in the ice is that it could be locked into these allotropes. So S2, S3 can form chains up to S8, and those are infrared invisible. And so it was like, okay, if we can't find it, 95% is unaccounted for. Maybe it's just going into these refractories or these chains that we just can't see. But this model is able to reproduce. It follows this S versus O chemistry. We understand a lot of the oxygen analogs experimentally really well. And so there's this thing to test now, what happens with organosulfur species experimentally. And so to summarize the theory part, we can reasonably model this depletion if this chemistry is similar, if majority is in its organosulfur phase instead of the expected carriers. And this is not based on experiments at all because there are very few solid state sulfur lab studies, and the ones that I'm about to show you today are the first of its kind. And so what we have here is that theory can reproduce observations with assumptions that haven't been tested empirically. So these are still the open questions with this background. If this is similar, why haven't we observed H2S, which is water sulfur analog? So that's really surprising because we know that this is common in water, or common in comets. So this lends the question, is this assumption even valid? Why haven't we detected any organosulfur in ices? So we have detected the most complex sulfur that we found is ethyl mercaptan, which is the ethanol analog. And still with all of this, we only have 4% of this, of the budget accounted for. So this is, can they even be formed in ices? We have seen it in our comet, but how does it form? It hasn't been confirmed yet. And also, why don't the models show that this refractory component is a significant reservoir? Like, is that even able to be formed in interstellar conditions? Could other refractory grains be the significant carrier instead? So all of these questions need to be tested empirically. So the way that these connect to our experiments is that organosulfurs have been detected in the gas phase. They cannot be formed in the gas phase because these super complex molecules need to be formed in the ice to even have the abundances that we detect in the gas. So if something has been detected in the gas, there must be some formation pathway for it, which needs to be tested empirically. And then theory-wise, what we can test is, can organosulfurs be this sulfur sink? And does O versus S chemistry proceed similarly? And so this is what majority of my dissertation has been about. And this was just to set the context. I wanted to, so since some of you might not have seen what these experiments are like, I wanted to briefly talk about the experimental methods and also motivate why methyl mercaptan. I first want to start with just the Astro 2020 decadal survey, because this happened as I was starting grad school and was a huge motivator for why I designed a thesis around this. And it talks about, these are just the specific parts that I really wanted to emphasize, that we basically, it said the conclusion for this decadal survey was laboratory astrophysics is essential to interpretation of astrophysical data, and it must be regarded as a high priority in order to maximize the scientific return of all these missions. So I hope that in the previous background explanation, I've explained why we need these experiments. And then why organosulfur? So these are just some of those ice constituents with respect to water ice towards YSOs, or young stellar objects, and comets. And we can see that both formaldehyde and methanol are pretty abundant across both. So methyl mercaptan is thought to form like methanol. It's both abundant, well characterized, and it has formaldehyde as an intermediate. Methanol is detected towards all evolutionary stages, and its experimentally backed models can effectively reproduce observations in the gas phase. CH₃SH, on the other hand, isn't well characterized at all. It lacks fundamental desorption behavior, formation, and destruction mechanisms. But it's the simplest S-bearing comp, so naturally we would assume that methyl mercaptan could be a model for larger organics. And also, we can study H2CS by way of studying methyl mercaptan, which is the most complex molecule detected in disks. So this was the reason why I chose methyl mercaptan. Briefly, I just wanted to show my lab mates and our experiments. All of them have really funny names. It started off with Space Cat. So if you hear me say any of these, the space always stands for Surface Processing Apparatus for Chemical Experiments to Constrain Astrophysical Theories. But I'll talk about Space Kitten, which is the tinier version of this, a little bit more. We have 4. They're called Space Cat, Space Mouse, Space Tiger, and Space Kitten. And so we have 4 of them. This is just one that I'll show, which has like the simplest, it's a simplest setup. So just gives you the base, what you need to run an experiment. The base pressure of these chambers it can range from 1 to the 10 to the minus 9 to 10 to the minus 11. So Space Kitten's base pressure goes to 4 to 10 to the minus 9. It's a closed cycle helium cryostat that gets it down to around 10 Kelvin. Our most powerful one gets it down to 4 Kelvin. There's a cesium iodide window, so this is transparent to IR, and that's where we grow our ices, so it's a substrate at the center of this chamber. There's a temperature controller that we can use to control the ice matrix temperature. This is an FTIR, which gives us the infrared spectra, which is our first data product. And then there's a quadruple mass spectrometer that gives, basically characterizes what's happening in the gas phase. And those result in what we call temperature programmed desorption curves, or TPD curves. And most of the first set of experiments that I'll show you will all be about these TPD curves. So in essence, what you're constantly monitoring the ice phase and the gas phase. So the moment some feature in the IR disappears, you should expect to see it in your QMS signal. So it's a way to tease out what actually is forming and what is desorbing, and monitor this gas grain interface easily. So I first want to talk about thermal desorption kinetics and entrapment results. So the fundamental properties of ices, the most simple of it is thermal desorption. That's just telling us, when does it desorb off grains? What temperature does it sublimate at? And that gives us its binding energy. And the binding energy is important to planet formation theorists because it allows us to determine the snowline location in a disk. And the snowline basically determines this gas grain boundary, and it is directly governed by this binding energy. However, ices are not single components, they're a mixture. So the most complex, or the most abundant of these is water. So one of the things that we look at is, how does this desorption get affected when it's mixed with water, when it's mixed with more realistic, what we call astrophysically realistic mixtures. And what we actually find in other studies in our lab is that, or in other studies in experimental astrochem, is that water can effectively entrap molecules, in that molecules that desorb before water desorb with water in the end. And so that's something that I wanted to check with sulfur organics. And it's important to know what can be present at this water snowline, because this is where planetesimals are able to overcome its meter size barrier. So to know the chemical inventory available for these planets at this meter size barrier, at this snowline, is important to know what can be inherited by the planetesimals. And so, as I mentioned, a lot of entrapment studies by our group members show that this is not matrix dependent, and it's effective for several hypervolatiles. So molecules like CO, methane, a lot of noble gases, they desorb, they're about 60% entrapped generally. So all the work in the following slides is in a paper I recently submitted. So it's about the fundamental characteristics of methyl mercaptan ices. So I just want to illustrate what I mean when I talk about ice matrices, just so it makes sense. So a pure one, this is methyl mercaptan, and also these are just molecules for illustration. It's not actually how it would be arranged in a matrix. But when I say a pure one, it's just layers and layers of methyl mercaptan. When I say layered, I'm talking about a water base and then a single or a submonolayer of methyl mercaptan. So actually for the pure, we call it multi-layer, so it's multiple layers, and layered excipients are single layer. And then you have the mixed where it has been pre-mixed and deposited together, and it is arranged in whatever lowest energy state it could be in, which is really hard to model. So the properties for each ice is the relative compositional ratio and its thickness. So you'll see a lot of these next slides will have monolayers, which is considered 10 to the 15 molecules per centimeter squared. And each of these ice matrices is expected to have different desorption kinetics or TPD curve profiles. So I just wanted to show just illustratively what an expected snowline or desorption front would be for different ice types. So over here, we would expect the water snowline to be around 1 to 2 AU for, or 1.5 to 2 AU for a solar type disk, and a pure volatile snowline at around 8 AU. But if a molecule is entrapped, you would expect some of the molecules that were expected to come off way later in the disk or way further out in the disk to be available in the solid phase at the water snowline. And what we quantify here in lab terms is entrapment efficiency, and that's the percent of volatile entrapped over the total amount of H2O that's inside. And that's about 60% pretty consistently for all hypervolatiles. So molecules are effectively entrapped in water matrices, and that shifts the snowline inward. So a TPD curve is basically the desorption rate or the QMS signal as a function of temperature. So to orient you here, I just have multi-layer methyl mercaptan versus methanol. So on the x-axis, we have temperature. On the y-axis, we have desorption rate. And so what we can just see here, what I just wanted to point out here is that methyl mercaptan desorbs before methanol. And that just means that methyl mercaptan is more volatile. And yeah, so this is just tells us for pure substrate, what temperature does a molecule sublimate off their grains. So when I go to pure versus layered, so the top is what I just showed before, and the bottom is a submonolayer or less than one monolayer on top of a compact water matrix. So when I say compact water, it means that we have deposited it at 100 Kelvin, so there's no pores. It's basically all compact and things cannot go in. And so what's really interesting here is that methyl mercaptan is indifferent to whether it's in a matrix by itself or in a matrix on top of water, which was quite surprising because if we think that methyl mercaptan is similar to methanol, we would assume there would be some sort of weak interaction between the sulfur and the thiol or the SH group in the methyl mercaptan with respect to the water. We thought it would orient, so this was really surprising for us just at that level. But what we can clearly see here is that methanol is really affected when it's in on top of water. So it's able to hydrogen bond to the water matrix. And it basically hugs that instead of, it basically comes off with the water in the bottom one. I can't really point with my cursor not being able to be seen, but I don't know if they're a laser pointer or something.
Yes.
Okay, super cool. Yeah, so I'm just talking about this hugging over here. So binding energies can be a proxy for sublimation fronts. So it's well described by this equation over here. All that you really need to know is that the left-hand side is the desorption rate from the TPD curve, and then we fit for this E desorption, which is the binding energy. And so what to note here is that on the left, I have the multi-layer curves for methyl mercaptan, and on the right, I have it for methanol. And what we see is that this is indifferent to, so on the, over here is like layers. So we have tens of layers to 100, and this is indifferent. So the binding energy is indifferent to the thickness. And so we basically fit this equation at this part of the curve where all of the curves align. There's a couple different ways to estimate this binding energy and this attempt frequency. This, I did not mention that in the previous slide. The new is also important in that it's basically telling us how many attempts does a particular molecule, if you think of it as a potential well, how many times does it have to vibrate in order to effectively come off. And so one thing to note is that these values are degenerate, and there's a few ways to estimate it. And so one of the parts of this paper was also validating this new method to basically account for, model this new and binding energy. So the empirical fit is that we just let it fit for both and find the best fit. There's a harmonic approximation, which assumes this molecule is a point mass and it's just vibrating. And then there's this new method called the transition state theory, where it counts for the rotational and translational degrees of freedom. And this is more important for larger molecules. And so bigger molecules, like methyl mercaptan, we assume are not well described by point masses. And these are just the two equations. And all I wanted to point out was that we need to include these two partition functions. And so on the top, we have just the empirical fit. And we see visually it looks good, but when we look at the errors, it's pretty bad. Over here, we have the harmonic fit. And we can see visually it does not fit to the this curve part. And for the TST, we find that it fits really well. And so what I ended up arguing in this paper is that transition state theory is the best out of these three leading methods. And we should move forward, model it using this. And so I motivate it for both methanol. And so notably, this method actually affects previous literature values of methanol and shifts its snow line kind of significantly by like 4 to 8 AU, depending on some assumptions. And another thing I wanted to check was, does this TST approximation vary as a function of thickness? And we see that within our recommended errors, there's a slight dependency, but not enough for us to for it to really matter thickness-wise. And so this was just one side result that we present that we should think about these molecules not just as point masses. And then this is where it gets a little bit interesting. For submonolayer experiments, what we see here, we have a multi-layered curve for both. So here we have methyl mercaptan, here we have methanol. What we see is that it doesn't matter for the submonolayer experiment for methyl mercaptan, whether it's on top of water or not. And for methanol, it basically still hugs that compact water line. And because we're not able to distinguish whether this is due to entrapment or whether this is due to actual binding, we're not able to get submonolayer binding energies for methanol. But I want to note that here, this is whatever is on this little bump over here does not change even as these values go up by a little bit. And so this is effectively what can be entrapped in the top pores, nanopores of a compact water matrix. And so since these basically do not change even from like 0.2 to 0.25 to 0.8, we basically consider this negligible, and this is just further will tell us how effectively sulfur, this sulfur organic can go into the water pores. For submonolayer regimes, we can't fit for a single binding energy. We have to fit for a distribution, and this is due to the ice topology. It's going to have different orientations, and so molecules can go on top, arrange themselves differently. And so we basically fit for the thinnest one because that's the most ideal case, and we fit for this distribution. And what we find is that in the recommended binding energies, there's basically effectively no difference between methanol and methanol and water. And so just to highlight, and when this is one of the tables in the paper, and you have to use both of these you have to use a binding energy and a nu in pairs. You can't just use one or the other if you use it to predict snow lines. So we present both, and essentially it doesn't matter for methyl mercaptan what matrix it's in. Here we get a little bit more complicated. This is our fiducial 3-component entrapment. I did binary and ternary mixtures, but for more astrophysically realistic, I have three components. I have methyl mercaptan, I have CO2, and I have water. And so on the top, it's both for like around 80 to 90 monolayers, and 1 to 2 to 11 or 12. And so pink is methyl mercaptan, blue is methanol. And what's really surprising here that we note immediately is that nothing is coming off for methanol at its pure desorption temperature. All of it is coming off at what we call this volcano desorption. And this volcano desorption has to do with the ice matrix restructuring. So that's shown by this little bump over here. So essentially, when the water matrix is restructuring, it allows for some pores to become a little bit big. And there's usually this immense increase in molecules that are entrapped that come off. And so we can see that happen for methanol as well, but we do see some of this methanol coming off at its pure desorption peak. And so this was a little bit surprising. And we note that all of it is basically coming off at this volcano and none of it is coming off at this co-desorption, which is very different to this methanol peak that we see. When I look at it in so over here, let me just orient you. I have very thick binary mixtures. So that's methanol to, or the methyl component and its water, and then methyl component and CO2 and H2O. And so when we orient ourselves from top to bottom, we're going from very thick, very dilute to very thick and more volatile rich, so more CO2 rich. And so until we get to the CO2 rich components, basically nothing is coming off for methyl mercaptan. Literally all of it is coming off at this volcano desorption peak, or after in the case of this thick ice, which has never been seen before. This was so surprising. I had to repeat some experiments just to even check, like, what is going on? Why is this happening? And in contrary, for the two fiducial ones for methanol, I just show that we have a little bit of both, but I have another plot that shows this very thick, very dilute in a little bit of a manner. But this was really surprising to us. No matter what, methyl mercaptan is entrapped. And the reason this is surprising is that I already proved to you earlier, it does not bind to water. Why is it only coming off at this peak? So what's curious is that it doesn't bind well to water, in that it doesn't, we saw the binding energy, it's coming off at its regular desorption temperature in both pure and layered cases. But in the mixed, it is coming off at this volcano, but it's never coming off at its co-desorption. So this was really surprising. We were trying to figure out, why is this the case? And I wanted to see if I can deduce this difference or effect computationally. And so I do some computational calculations using Gaussian 16. So this is just showing, this is methyl mercaptan, and this is methanol, and this is to size. So it's size based on its covalent effects. And these are just dimer calculations, which are just two components. And this is the most energetically favorable conformation for these. And the dashed line represents where it's bound. And these were the results. And generally, dimer calculations have been shown to match experimental binding energies pretty well with some conversion factor. But for these, it doesn't even make sense qualitatively. So we can see this computational, and this is just the method I use to calculate these. And so just relative to these two, we see that methyl mercaptan and methyl mercaptan to water, we should expect a higher binding energy for, have we got on time?
Still, what, 10, 15 minutes?
Okay, so methyl mercaptan to methyl mercaptan, it's showing that there should be around 1,000 Kelvin difference, which can be several AU if you convert this to protoplanetary snowline disk space. So that doesn't make sense empirically. And then when we look over here, we find that methanol to methanol should be a little bit more should be higher than methanol to water. And even though I didn't calculate this experimentally, we've already seen that it shifts so dramatically. So even qualitatively, these did not make sense. The only thing that made sense was that methyl mercaptan to methyl mercaptan, the pure ones, this one was less than methanol. And so this was really surprising. I tried different ones. I talked to some of my pure computational colleagues, and we were very surprised. And what we basically have found is that the size effect of methanol or the sulfur molecule, it basically can't take advantage of the ice topology in order to bind to itself in the most energetically favorable way. And this is further validated by what I said is the most thick and most dilute. And so what we see here is at this volcano desorption peak, once it comes off, and these markers are based on the fiducial ones. So just for ease of like recognizing patterns. But what we see here is that methanol, the moment that it escapes, it's still able to diffuse through the water matrix and come off consistently. Whereas methyl mercaptan, once the pore size opens, all of it comes off. And that's because it doesn't bind to this water, the water well. We've already established that. But once you get to thicker ices, more of that water has to come off to open this pore size, and it basically just comes off all at once. And this was the first time we were able to constrain the pore size of water. And it's basically between methanol and methyl mercaptan, which are only 15% difference in space, which corresponds to about, or the size ultimate size is like about 3.9 angstroms. Basically, between these two, it's like kind of a very binary effect. If you're smaller than it, you can come through the pores. If you're not, you have to wait for the ice to restructure to let enough of this out. And this is the first time we've ever seen such a size effect, the first time we've ever been able to constrain the pore size. And if this is happening for some of the simplest complex molecules, if more complex molecules are actually formed in ices, those we would expect to always be present at the water snow line. So this is just a summary of the main results. I use these binding energies to just predict for a solar type disk just where we would expect the snow lines to be. And what we basically illustrate is that based on whether it's pure or layered or entrapped, we would expect it to shift by a few AU. And something that's still a little bit debated is whether these molecules form on top of water or form with water. And what we would say is that if we find molecules that are more entrapped, more like bigger than methanol, found beyond the water snow line for a particular disk or a particular observation, we wouldn't expect that to be formed in the water. We would expect it to form after. So it's a way to basically, the fact that it's 100% entrapped, we can say something about the formation history of these molecules. And that's one of our main results. So basically, it'll affect the snowline locations and disk models based on when it's formed. And one of the things we want to check is, can this extend to larger molecules? So ongoing experimental work is formation and destruction. And I wanted to highlight why a lot of sulfur experiments have not worked before. And it basically, sulfur is very corrosive and just dirties the substrate pretty badly. So on the left, we have one of our substrates just cleaned. And this is after a few sulfur experiments. And so this will affect your IR signal pretty significantly. It's really hard to deal with, and you kind of have artifacts. And so some of these formation and destruction experiments I've had to pause because I needed to figure out how to basically deal with the this kind of corrosive effects. And so these are still preliminary, or I'm still working on them and getting more reliable data. Methyl, in terms of formation, methanol is formed in a few ways, 3 ways. There's successive hydrogenation of CO, so you just add H to CO molecule, CO ices. There's irradiation of water and methane ices, and then there's oxygen insertion. So one of the things that I wanted to do when I started was investigate the analogous sulfur-bearing reactions in the laboratory. And a previous computational study that looked at the reaction 1 found that this is way more favorable than it is for methanol. And so what the prediction was for these was that methyl mercaptan should form more effectively. And this was something that I wanted to test, but it's very hard to isolate CS. So I started with where I could just buy the molecules itself. So I started with H2S and methane. And this is just an example of how we characterize these formation pathways. So a fiducial experiment is like 300 monolayers, 1 to 5 of H2S plus methane. You irradiate it. And you form one of the ways that we can actually so because I showed you the IR, the substrate is corroded pretty badly, our IR data are really horrible, and we can't really quantify based on IR, so we have to quantify based on the TPD. And based on this, the way that we can actually determine what molecule is forming, because we don't have the spectral signature, is by doing what we call an isotopic substitution. So each experiment that I do, I ran it with the 13-methane as well, and you would expect it to shift and these TPD curves to match. So these are for a particular mass to charge. So I confirmed that it can form, the desorption temperature matches, and I'm still quantifying the relative rates. And none of these are done in methane-dominated ices. So here's an example just to show you what I mean by this isotopic shift. So in the QMS, all of these molecules can fragment into different subspecies. So it can go anywhere from mass 46 to mass 48, which are the most dominant for just 12 methyl mercaptan. And so when I shift it by 1, you can see that these curves match pretty well. And so this confirms that we've formed it. And another way, another way that we can actually look at this is by integrating at the peak and comparing it to the NIST webbook. And so this is just the fragmentation pattern that I was explaining. And this relative fragmentation pattern for these matches. But I do want to point to you that we get this enhancement of 46 and 47, which is H2CS. And this is similar to what happens with H2CO. And so this is surprising because the H2CS that we see in discs, we have tried to search for methyl mercaptan in these regions, but we're not finding it. And so this suggests that if we form some of the H2CS, we should see some of the methyl mercaptan with it, but we don't. And so this kind of likely means that H2CS that is seen in discs is formed in the gas phase. So this is another way that experiments kind of help us rationalize observation. And just simply, I haven't been able to do a bunch of these destruction experiments just because of figuring out our IR issues, but this is a sample irradiation spectrum. And what we find here is basically the same thickness of molecules and equivalent electron energy, electron fluence. And basically what we find is that all of the methyl mercaptan is destroyed, whereas very little of the methanol is destroyed. And so this just means that methanol methyl mercaptan is dissociating more rapidly. And so in terms of that summary is that methyl mercaptan is formed less efficiently and destroyed more effectively. And this is the full stability analysis that I'm doing for methyl mercaptan relative to methanol. And the significant part of this is that this is a way for us to really probe this S versus O chemistry that hasn't been done before. And this also shows that the early results show that methyl mercaptan is likely not the sulfur sink. One of the things that I wanted to bring up was that in the H2S plus methane experiments, I form a lot of S2 and S3. I can't look at anything more than that because our QMS resolution is only up to 100 mass to charge. But that's surprising compared to what our model predicted. So one of the things that I want to quantify is how much of this, where is the sulfur going? And that's still what I want to do. But this is basically the experimental portion. Oh, that should not have. I wanted to basically highlight in terms of the results. The laboratory experiments allow us to interpret observations and gives us a potential molecular target to look at. So one of the things that we are going to look at is could thioformaldehyde be indicative of gas phase formation, and could it be locked up in sulfur chains? And And my experiments give us reaction rate network inputs. And I want to basically apply those to the current gas grain reaction networks and basically see if I can reproduce what Loss and Caselli did with some of this data. I don't know how we're doing on time, so I have some observational stuff, but I won't get into it, and I'm happy to talk about it later. But I just wanted to leave you with probably this summary in terms of future work. Essentially, what all these experiments are showing is that this S versus O chemistry is different, likely due to sulfur's size. And that's pretty interesting because I think we can exploit this difference in a lot of ways and extend it to larger organics. That could be, that could tell us something about different formation pathways and locations where these molecules could have formed within a disk. And another thing is I have all of these mixed spectra now that I want to apply to observations. So one thing I want to highlight in the infrared spectra is that in mixed ices, we do see these spectral shifts and broadening, and this can be applied to archival. So now that I'm building up a spectral database, I want to apply it to JWST observations to infer mixing ratios and see if I can actually find hints of methyl mercaptan. And this S substitution for O is critical in a lot of early Earth and origin of life applications. So looking at this comparative chemistry framework and be able to say something about sulfur with respect to a really well-known element is, I think, the way to go in order to understand this missing sulfur problem. I'm happy to take any questions, and I hope this makes, yeah, thanks for your time.
So we have time for a few questions, and for audience online, if you want to ask a question, please raise your hand. And do we have any questions in the room?
So this is about the experimental setup. So I was curious about like how long it takes to run it, and do you control the temperature on the substrate itself, or can you know, is it more of an environment thing? Is it the vacuum too low to do it anywhere other than the substrate that you're putting the sample on?
Am I affecting the temperature anywhere else?
Yeah, in the setup.
Oh no, it's just at this at the substrate. I think there could be other ways to affect the chamber, but we are only probing like truly on the ice part. But we can affect, we can change the pressure of the overall chamber to model different atmospheric locations. So one of our new experiments is trying to see how these molecules are formed or in different environments, not just like super ultra high vacuum, ultra low temperature, but model, like, for example, icy moon conditions or different pressures like that. So we are looking at how to change the base pressure itself and see how that affects the chemistry.
Yes.
Yeah, questions. I'm really interested in starless cores and pre-stellar cores with very cold initial phases. So have any of your experiments made significant revisions to like the binding energy that could affect like reactive desorption to get some of the complex organics off, and they have a chemical reaction that just releases enough energy to go become binding energy?
Oh, wait, sorry, can you repeat?
Yeah, so for one of the ideas for how we get some of these complex organics at like 10 Kelvin, you don't have all this irradiation and it's a very cold shielded phase.
Yeah.
Is it maybe chemical reactions on the surface of the grain to provide enough energy to combine there? So I'm curious if there's been what kind of revisions you've had, like for instance to methanols to its binding energies, how that might affect those types of theoretical calculations, I guess, people are doing for reactive dispersion. Yeah,
so I think that I haven't personally thought about those super shielded locations, but I think that you know, the binding energies, like with the TST model, those itself are entirely based on theoretical calculations. So one of the things that we're proposing to do is like basically model it theoretically and basically account for all of these. I think just the rotational degrees of freedom will I think that will impact more based on than actually this what's caused by reactions. I think just our understanding of the molecule itself and this attempt frequency is going to shift it, because that's what I saw with methanol. I shifted it by 1500 Kelvin, which is a lot in like binding energy. So I think just the physical model of the molecule will affect it more than the actual chemistry. So that would be my suspicion.
Yeah, I got a second question. Maybe somebody else wants to ask.
Yeah. There's no other people. That's question. You can follow.
I'm really also interested in how deuteration would affect your results. So if you had a change or plans in the future to look at deuterated isotopal logs.
Yeah, so one of my lab mates, one of her thesis is actually looking at the HD exchange, and she's looking at the H2O plus CD4. So Alexia Simon, who's one of my lab mates who did the entrapment stuff, her work is going to come out soon with the deuterium exchange, which we do see affects it pretty significantly. So the difficult part of that is actually making sure this exchange doesn't happen within the gas line. So it's really difficult to actually make sure that the exchange that we're seeing is happening in the experiment itself and not randomly. So those experiments are really, really difficult to do.
I hope I can get on your schedule to talk with you tomorrow.
Yeah, of
I'll
course.
just say one quick fun fact. We've just been finishing a survey of deuterated molecules in Starless cores. And it's fun to see you talk about gas phase formation of H2CS because we have 100% detection in HDCS. We got it for free and it totally surprised us.
Whoa.
And so we're trying to understand where it comes from. So can't wait to talk to you tomorrow.
Super cool. What's your name?
Yancy Shirley.
Okay.
Yeah.
Thank you.
Yeah, I also have a question. Maybe I can start with the technical one. You said that in your experiment, you irradiate the sample. What is your light source? Like, what are the characteristics of the light source?
So right now I've only shown you electron irradiation. So that's just our electron gun, which is around 2000 keV. 2000. I'm sorry. I have to check the specifics of the actual thing. And in terms of our lamp profile, I can pull that up to show you the emission spectrum. So we do have a VUV H2D2 like lamp source that has both. I have to double check the nanometers or that it's emitting at. But the reason that I initially moved the H2S methane to electrons is that CH4 needs a lot of Lyman alpha to be able to destroy, and our lamp source just doesn't do that. So electrons are more effective because they're actually breaking apart the methane. And so depending on your molecules and its absorption cross sections for the UV, you basically have to change your irradiation sources. So that was the reason why I moved to electron irradiation, because I wasn't seeing much product for the methyl mercaptan. And I thought initially that is because my irradiation source was just not effective. But even with electrons, which should be breaking it, I wasn't seeing much. So that was really surprising.
Okay, cool. So if we wanted to look for these sulfur molecules, I know we have trouble detecting them, but if we wanted to dig into the spectrum, where should we look at? Like at which wavelengths? Sorry, I cannot translate.
Oh, okay. Yeah, sorry. This is I should have plotted it in. So it's around 3.95 microns.
Oh. This
shift, yeah. So around, yeah.
And with respect to methanol, how significant the signal you think might be?
For methyl mercaptan?
Mm-hmm.
Honestly, I have no idea. And I would assume it's really, really weak. But actually, one former member of our group just validated this method of different mixing ratios to identify mixing ratios in JWST spectra. So that's it's by Jennifer Bergner, just got published a couple of months ago. So that's the method that we're kind of going to follow and try a bunch of different ratios and try to make this spectra available so people can use it to apply to their data. But since we haven't even detected it at all, I have no idea. But I think methyl mercaptan to methanol in the gas phase is around 0.01 to 0.2. So if I think it should be somewhat detected, but we're not seeing even H2S, for example. So it's a little bit surprising. And I don't know how well we can translate gas phase ratios to ice now. So that somewhat answers.
I have last question, if I may.
Sure, go ahead.
So, I did not quite catch what caused the differences between your experiment results and the empirical expectations, like this temperature difference between methanol and the sulfur version of methanol.
Yeah,
How-
so
If you could explain that once again.
yeah, I can. So basically, the conclusion is that our computational, so I think you're talking about this, right? And so dimer calculations generally are pretty well for less volatiles. It explains these binding interactions really well. But for mercaptan, these sulfur topological size effects, like this is just two molecules, but if you're actually going to do it in a matrix, which is very computationally expensive, which is why people assume that dimers can actually be a good assumption, and they've tested this across a bunch of volatiles. But since we're what I think is not happening, or I want to try and do a matrix, but I've never done this super complex matrix because it's very difficult to confirm that it's that kind of structure, especially for large molecules. But what I think is happening is that it's not able to consider these large covalent, like actual sulfur, the size effects very well. And so these orientations, when it's in a matrix, are probably not as powerful as it can be. And so it's like a topological constraint. And that's kind of confirmed by all these different, this series of experiments that I did with the pure, layered, and entrap. And so one of the things that we conclude is that we currently cannot model large molecules computationally really well. And that's something to basically consider. How can we actually reconcile the two? Because something that so I was trying really hard to match these calculations with my experiments, and Karin was the one who told me, like, your experiments are the ground truth. The model should actually try and fix this. So I was actually thinking about it the other way pretty hard. I was like trying a bunch of different calculations, and I think it's just our limitations with modeling, right?
Yeah,
Yeah,
I
that's
wanted to, I wanted to follow up, very nice talk. Wanted to follow up on the main result, just to be sure that I understood.
Yeah, of course.
So, so your results suggest that any molecule that is similar or smaller than this methanol will have its own snow line, even if it's embedded in a water matrix. But if it's larger, then it will have the snow line of water. Is that the main result?
Yes, and that's
Okay.
if it formed when water was also condensed into, if it's not and it's layered, I think we have to look at the pure binding energies or layered binding energies. But if we think that it was formed within a water matrix, which I think likely it was, then it should be present at the water snow line. And I think since we are able to constrain this pore size, I think this can be extended to larger organics, and that's something we want to test in the lab itself. But this is the largest molecule we've looked at in the lab right now. So the fact that this happened, yeah.
Essentially, as a consequence, you would expect a number of larger molecules to be desorbed at the snow line,
Yeah.
in addition to water. But it seems like when you show this curve of the methanol, that there is also significant methanol coming out of the water snow line.
Oh, there is.
Yeah.
Yeah, there is, but it's not 100%.
I see.
And that's the thing. So I think we can't really say much about smaller ones. We can model it as much, but it's pretty similar to what we see for the other volatiles, where it's around 60%. So we would still see 40% of it have its own snow line. But the fact that this was kind of really binary for the methyl mercaptan was the significant thing, and between methanol and methyl mercaptan, the size difference isn't that much. So between that, that basically gave us this pore constraint. Yeah.
Okay, we're at the top of the hour, and the speaker will stay here for today and tomorrow. And if you're interested for further discussions, you can use the sign-up sheet that we shared in our Origin seminar link. And let's thank our speaker again. Thank you.
And I would add that we are going out for lunch now.